Sí.
So how far I can go? How far I can go?
Yeah, you can.
Hmm?
Yeah.
This
Yes,
up to
yes.
this?
Yes, yes.
On this part only.
Yeah.
Okay. Okay. So let's start. Okay. Sorry. Okay. So this part, as you can understand, this is bit non-trivial. This for continuous cases, but I just introduce it because in few minutes I will discuss some of the practical physical realizations in experiments, and one of the experiments uses this concept. So for that on purpose only I introduced it. Apart from that, the whatever we have discussed so far is sufficient for the rest of the talk. Okay, so now I just for the just state some results. I mean, not in details. For examples, you can look at. So, like as I said here, it could be the examples. I mean, this you can think of like this kind of models essentially is useful to practical realizations. So let's say you have a harmonic trap, you have a single particle. So this is how this Hamiltonian changes. Okay, so people have realized, you can look at these papers. Okay, so they have realized again in auto cycles. So you see, you can understand now this is like kind of this various change of this frequency. Okay, so these compressions, then you have isochoric processes and all that. And in these strokes where you have also this heat exchange, so that they have introduced some form of electrical noise which provides energy. We'll show, and as long as you are abide by this adiabatic limit, that means extremely slow. Okay, so then essentially you get this kind of equations for the auto cycles. But as I said, that compared to this classical adiabatic processes, quantum adiabatic process is fundamentally different. I mean, classically the adiabatic process is fast. Quantum mechanically it has to be slow process, quasi-static process. So definitely, although it has efficiency, if in terms of power you don't get much, so that's a problem. So when you implement such kind of auto cycle, as I said, auto cycle has an advantage because it has adiabatic n omega plot. It involves only heat and work. So in that respect, it is best to implement, but also has this problem. So because of this adiabatic problem, it is important to optimize such cycles. Okay, so this is an entire field. Okay, particularly Adolfo Del Campo pioneered. If you are interested to look at. Okay, so that's what is in brief you can think of like a shortcut to adiabaticity. So the whole idea is that, is it possible to minimize the time required to complete these adiabatic strokes to optimize this cycle so that you have a finite power and so on. So that's the shortcut to adiabaticity. Okay, another this is one of the thing. Okay, and second thing is that in the context of this quantum signature, instead of if you have a single particle, if you have a multi-particle, may depends on the statistics of these particles. Let's say if it is whether it's a bosons, fermions, and this is this reference where these are like the phase space distributions. Like even if you don't introduce to this quantum phase space Wigner distribution and so on, even classically it's just the Wigner, these quantum the classical analog of that. So it is classically distinguishable particles if you have two such bosons in this case. So you see that the distributions is along this diagonal, it is elongated. That means the bosons, try to be together. On the other hand, the fermions, they repel each other. And what they have, shown again, I'm just stating as these kind of, the entire idea of this study of this quantum thermodynamics, as I, from the very beginning, you see that whether you have really some quantum thermodynamic signatures, maybe you don't violate, but does it have some, you can design some systems where it has some features which is not, available in classical settings. So this is one of the kind of signatures where the statistics of these particles can play a role, can be significant, and they have shown like bosons outperform fermions in terms of performance, in terms of engine. And also I mostly discuss engines, but again, you can understand, like even if you recall this SSD model, you can also have a refrigerator analog. If you have, instead of the signal, what is getting out, if you have invest energy like in a refrigerator, then you have, extract heat from the cold bath. So the refrigerator is exactly the reverse of this one. So I'm, therefore I'm not discussing refrigerator in particular, but essentially, so mostly discussing engines, but refrigerators, you can extend it in similar way. So what they have shown is the boson outperform fermions. That's the results they have shown. So in that way, it is kind of quantum signatures. Okay, as I said, like this is kind of another fields, and so far, whatever the way I have defined the heat and work, there is a very, entire field, what is known as the stochastic thermodynamics and fluctuations in finite time engines and so on. Okay, where so the entire, field are there, right? People are interested to define heat and work in a very different way that we have defined. Okay, so here everything is defined for a small systems. So all these heat and work. Okay, so again, I'm just not getting, these, I'm just getting into this, giving these references. If you are interested, Campesi, Hengi, and they have, introduced a lot of things. So there, these heat and work are defined in terms of stochastic variables. So these efficiency will also be stochastic. Then the probability you can define, okay, the having this efficiency in a probabilistic term. And they have, also interested in, is it possible, okay, whether work is an observable or not. Okay, so is it possible to define an operator for that? I mean, all sorts of questions, interesting questions this has been. But again, I mean, I am not getting into that domain. But these are, as I said from the very beginning, there are different approaches. So we have taken in the most, simplest one, which is in close analogy to classical thermodynamics, where we have these stroke cycles, and then you have these various processes, and then definitions of heat and work, how to do that. And these definitions, whatever we have discussed, is particularly, I will show you in a minute that it has been used in real situations, practical situations, people have used it. But before that, let me, so trace these few things like this quantum thermodynamic signature. This is, you can think of one of the quantum thermodynamic signatures. Another is this one. Okay, there are others as well. So I have just shortlisted maybe, one or two. This is quite interesting proposals. This is the reference. So this idea is the following. Let's say you have, what do we mean by quantum thermodynamic signature here? Here also they have constructed such kind of engines. Well, auto engines. Okay, so in a particle in box problem. Okay, so it's just a 1D particle in box. It's a theoretical proposal, some experimental, theoretical work with some experimental proposal also there. So here you can have these strokes. In order to realize these strokes, you have these volume compressions and the expansions. How to realize that? So classically, if you have a gas, okay, so in a 1D box, okay, put a particle in box, okay, so the volume compressions you can think of that putting some barrier. Okay, so in experiments you can put some delta functions, infinite strength delta function, laser pulse, so which separate one. So this is kind of analog. So on the other hand, classically, if you look at the the auto efficiency is given by these expressions, where gamma is the ratio of this, specific heat, where R is the compressibility factor, this volume of this, cold and the hot cycles. strokes. This is now you can immediately see from these equations, in order to get a non-zero efficiency, classically volume change is required in order to perform work, right? I mean PDV. So if you do not have any volume change, you do not have any work, mechanical work. On the other hand, and if let's say this compressibility, if you have this working fluid which is incompressible, that means this R is exactly 1. Okay, so then you get efficiency to be 0. So for classical systems, for classical engines, you only get, it works as engines if you have incompressible fluids, so that you can have a volume change, expansion and compression works. On the other hand, for an incompressible fluids, this is classical efficiency is exactly precisely 0. On the other hand, quantum mechanically, because what happens, what is quantum mechanically, even if it is an incompressible fluid, you may have end up with a non-zero efficiency. So that's kind of a pure quantum signatures you can think of. The reason behind it is the following: because thermodynamic behavior at the macroscopic systems mainly depends on the bulk property, that is the volume of the systems, not on the shape or the geometry. But at the very basic levels, when you solve particle in box, so then this energy gets quantized once you put, in Schrodinger equations, the boundary conditions. So the boundary conditions plays a very, very fundamental role. So if you have similar setup, okay, with these energy levels and the wave functions, once you put this infinite barrier in between, what do you get? Okay, so these, ground state and the first excited states, they become degenerate, So you have essentially this, and also you have these two levels once you put, okay, infinite barrier, isn't it? So you have essentially, when you have this one, you have this, okay, so you have this one, you have this one. On the other hand, once you put it, okay, so this becomes this and this becomes this. Right. So then these two wave functions have the degenerate. I mean, it's no longer different energy. So this has, same energy. So you can have like this or this, whatever way you write. Okay. So they have once you, putting some barriers, it will introduce degeneracy. So therefore, even in quantum system, if it is an incompressible fluid, even then you end up with some non-zero efficiency that you can think of a pure quantum effect. So this is what they have shown. I just state these results. Just, there are many effects, like even people looked at, like you have spins. Okay, so particularly in optomechanical systems, like in quantum optics, we have studied super radiance, cooperative effects. So that also you can think of, can have pure quantum signatures, like all spins collectively interfere with the reservoirs. So that what people have noticed is that the power get enhanced. Okay, so let's say you have n such spins. What do you expect? Classically, the power should get linearly, scaled, but due to this cooperative effect, it is non-linearly scaled. So in terms of power, you get a boost, but on the efficiency, you don't get. So efficiency is still bounded by these classical bounds, but in terms of power, you get some advantages. So that kind of, all sorts of, some of I just mentioned. Okay, so these two things quite interesting. So I just mentioned it. So with this, let's move on. So now let us discuss the last part. Okay, so here's some of the physical platforms, or many theoretical works, or with some experimental proposition has been done, starting from ion traps, cold gas, optomechanical systems, photovoltaic, superconducting devices. But only in these, there are some more, but okay, so particularly this review is quite good. It summarizes, both the theoretical as well as the experimental, whatever experiment has so far done in this field in last 5 to 6 years. So particularly these ion traps, names and MEMS, and these NV centers. So in these systems, it has been realized. So let us, let us briefly discuss. Although, as I said, I'm not, the technical details is not very clear. Okay, so let me, just tell you, okay, what they have done or what kind of cycles they have realized experimentally. So this is kind of the first experiment that I mentioned, single atom heat engine in 2016. So what they have done, like they have a calcium ion, it's a single ion trap, so linear Paul trap. Okay, so this trap has a geometry. It's okay, so it's a funnel shaped geometry. Okay, and so in the ion is trapped in between. Okay, and you have this trap is realized by pseudo potentials in the x and y axis. Okay, so this potential has this form of V of xy is equal to harmonic oscillators in both the x square, x and y directions, and the z axis along this axial along this axial directions, this atom can move. Okay, so there is two n cap electrodes, so the atoms can move along these z directions with a particular frequency of this. Now, this is as long as the system is considered or the working fluid is considered, and then they have like cold bath and the hot bath. How to realize that? So the cold bath, they what they do, like a laser cooling beam. Okay, so with this millikelvin temperature. On the other hand, the hot bath, in most of the experiments, you will see that essentially it's a electric fields which provides noise in the form of white noise. So that kind of acts like a hot bath. Okay, so then what they realize essentially is Stirling cycles. Okay, so engines is alternatively driven. So you have this bath is drive this, it's a driven system, so driven by heating and the cooling in the radial directions. So then you have similarly, as I discussed, n omega plot in one of the radial directions. Okay, so omega r is one of the directions. So and then you can think of, so it starts with, let's say, from here. Okay, so iron has some, it has some thermal width. Okay, so depending on these temperatures, let's say it starts with thermalized with the cold bath. It has some broadening, distributions. So it has some distributions. Then what you do, you just sign with this hot bath with the, this one. So then what happens? It's broadened. Okay, so the red one, it gets broadened. Then what happens? You make some weaker confinement so that this ion moves along the z directions. So this is kind of this work. Okay, in the systems, and then again you cool down with the cold bath. So again it is with decreases very schematically. I'm just for those who are interested in experiments, you can look at all these details. Then it is again bring back. Okay, so it has since due to this confinement there is a restoring force, so eventually you have these positions of these ions. Okay, so this is how it is, and there is some restoring force. And this restoring force, this is the restoring force. It is a temperature dependent restoring force, since you are changing. So eventually, due to this restoring force, it is eventually bring back to these original positions. Now this is kind of the fast, but again you see this Stirling cycles in the n omega plot. It's not looks good the way we plot, because the problem is here. This thermalization, the way they have done, it's not, the atom is not really get thermalized, truly thermalized. So it's not, the cycle is very distorted one. But still, this is quite fascinating, because this is the first experiment it has been done. And what they have computed is that the power output. Okay, so in 3 different ways, just to make their analysis consistent. So first thing they have done is like the area calculation. So this power is again the output work divided by the tau cycles. tau cycles, you can understand again, it's that these omega z frequency, so that defines the cycle time. And what is the work? You can again, as I discussed, like you have this E is equal to, I mean, n. Okay, so h cross omega n plus half. If you add also this half factor, so it is essentially 2n bar. Then okay, so h cross omega 2n bar plus 1. So then this dw, you can understand the change in this frequency. So it is essentially 2n bar d omega. So here that definition is introduced. Okay, here in one of the radial directions. So this area under the curve is kind of work you can think of. So this is based on this, they calculated power. Direct measurement, experimental measurement, because essentially it is these ionic motions is like an harmonic oscillators, damped harmonic oscillators. So they measure the amplitude of the oscillations. This is the damping, they experimentally measure. This is the frequency they know. So this is kind of a direct measurements. And they also have some analytical power calculations based on this, as I said, time dependent force. Okay, so use that. And then also they calculate QH from the entropy and so on. Well, so then this is what they have reported. So this is, but you can understand this is the extremely very small value because the argument is the following, since it is just a single ions, right? So if it is some macroscopic one, you can think of it is, at least if you just proportional linearly, even then it's as a macroscopic. And the efficiency is quite small, but still it is the first experiment. So that's it. Okay, so this is first experiment was in the ion trap. Yes, any question? Okay, so the first experiment is in the ion trap, and second is this. This is quite fascinating. As I said, very beginning. So there was this nano heat engines which exceeds, Carnot. So this was the first theoretical proposals, and later 2017 they made an experiment. So again, this is, from now on you will see all the engines. The first one is Stirling, but the rest of the engines you see Otto. And here, very excellent agreements with these data points, matches very well for the Otto, because there is you don't need to differentiate, heat and work for the individual strokes. So in that way, as I said, Otto is much easier to implement in physical situations, practical situations. So what they do is like MEMS and NEMS is a micro mechanical or nanomechanical, systems where you have essentially the Otto engine is realized by working medium consisting of a vibrating nanobeam. Okay. So, and the reservoirs are driven quizzed electric noise again. So again, you see that in all these examples, the bath is essentially mimicked as some form of electric noise. So this is the system. So it is a nanobeam of gallium arsenide. So with a doubly clamped in the two ends, and which vibrates with a typical frequency of this one. And then you have this squeezed noise. This is how they generate. This is what they mentioned, that they superpose two such white noise. Okay, so Xi1 and Xi2, okay, sine and cosines with these squeezing parameters with an amplitude A0. So that's kind of, this is what this is how they create this squeezed electric noise. And the sine, this, the system is subject to this squeezed thermal noise, and eventually it gets thermalized. Okay, so how do they define temperature in such systems? You see that these are the plots. If you look at in these different quadrature, if the amplitude is large, but this R is squeezing parameter is 0, it is precisely circle. Then but with the increase of this R, it gets squeezed, right? So then what you can define, like in both these quadratures, this temperature can be identified as the widths of these distributions. So you have an effective temperature, if you like, that in this direction it is T1 and it is T2, and then you can have an temperature, effective temperature T in terms of T1 and T2. So T1 and T2, so you have kind of a phase space distribution, I mean probability density of the quiesced thermal state with an effective temperature determined from this, and these distributions they measured with the interferometer. Okay, so they first subject this nanobeam with this electric noise. When it's thermalized, they measures with interferometer, I mean the distributions along both the quadrature. From there, they determine this T1 and T2, and that defines, in terms of some effective temperature T. So that's kind of then in terms of this T, they calculated the mean energy of a nanobeam. Again, it's kind of an harmonic oscillator, so use that formula, okay, so to calculate this mean energy. And when they plot, okay, measure experimentally, so this is exactly in terms of this squeezing parameter, it satisfies very well. On the other hand, again, this volume is again frequency, if you like. So they put volume, and this one. So again, you see the cycle is completed with this. This is at these various, these points. These are how this distribution look like. Now, what they have shown theoretically, the proposition is that if you use such kind of baths, okay, you may go above Carnot. And so you see, here is the Carnot bond. This is what I discussed. Here is the Carnot. So this is what they have obtained. Okay, so that efficiency is this, and it is above Carnot. So this, when these papers came, so it has this, very, interesting title. It goes beyond Carnot and so on. But they also have a theoretical results. As I said, I mean, I gave one examples, particularly in the context of this Kali's paper, right? If you take into account all these effects, then it is not a violation of this thermodynamics. So you can have, because it is a non-thermal bath, so the Carnot comparison with the Carnot is no longer essentially, valid anymore. So you need something generalized Carnot. If you have something generalized Carnot, then it is you are okay with this. So all this sort of, all kind of interesting baths, the analysis could be, extended to such kind of, to find out whether it is possible to find some universal efficiency bound for all such kind of baths. And here, what has been done is essentially what I discussed at the very beginning, this entropy production, because reversibility and the irreversibility essentially given by this entropy production, which is the time integrated version of this in non-equilibrium classical thermodynamics. Okay, so the equality corresponds to reversible, inequality corresponds to irreversible processes. Now, in quantum systems, an analog of this one has been put forwarded by Herbert Spohns. Okay, is a mathematical physicist who also, okay, so this is kind of, you can think of, it's an equivalent version of the entropy production satisfying this. So where this capital sigma, you can, essentially identified as this. Okay, sorry, is a relative entropy of the systems. Okay, so this is how it is defined. Some initial state rho 0 at time t0. If the systems and the rho steady state, the systems eventually, reach some steady state by rho ss. So this is strictly, positive. So in that sense, this is the quantum equivalent of this entropy productions. This is based on, mathematically, it is based on this dynamical map, the master equations that you are studied, as long as it is CPTP map, trace preserving, then this inequality is obtained. So what is known as Spohns inequality in this community. Okay, so and this Spohns inequality, based on that, you can, like you do, like in classical thermodynamics, you get a bound. Okay, so based on delta S, change in the delta S, you have some inequality, which is essentially the form of the second law of thermodynamics. This is what you write. So you can have a similar kind of bounds, inequality you can even derive for if this bath is thermal. Okay, so this is very equivalent in the same spirit like we are familiar with the classical thermodynamics. So that's kind of a quantum analog, but as long as the bath is thermal. The question is, if the bath is non-thermal, then you can, is it possible to extend this entire concept even to non-thermal bath? Now this has been done, and these are the references. So these references particularly. So I mean, I just give you what it essentially says. You see, if it is a thermal bath, you have a working fluid, right? Then if you have a thermal bath, so then you have a circle, right? I mean, the distribution is, you can think of it, say, circular. It provides thermal energy, only QH. Then what happens? Out of QH, some amount, okay, of heat goes to the cold bath, and the rest you extract in the form of work. Okay. Now, if it is energy if it is a non-thermal bath, as we have seen, this it also contains some ergotropy. Okay, and this by definition, this is always positive. So a non-thermal bath, if you like, it provides two kinds of energy. One is kind of thermal energy, QH, and another is kind of ergotropy, which is not essentially, if you like, it's not kind of an heat, it's kind of an work analog. So it provides, because it's squeezed, so I mean, doing these unitary transformations, any unitary transformations is kind of an work equivalent. So therefore you can think of this one is providing some form of ergotropy. So it provides both this form of energy. Now, based on this, if you derive some bounds on this efficiency, one can obtain this one. Now, you see, this is quite interesting. If it is a thermal bath, this is precisely 0. If it is 0, then QH and QH cancels in both numerator and denominator. You obtained your classical bound, I mean, Carnot. On the other hand, since it is precisely positive, this factor is always less than 1, makes it, you have a higher efficiency for non-thermal bath. But as I said, comparing directly with the Carnot is not fair, because you have a different situations. You have a very different baths. Classically, you do not have such kind of baths. You have only thermal baths, and the Carnot is derived only based on that. If you have different baths, you have to derive that and then compare whether it is. Now, quite interesting is the following. So you see, this is eta, any efficiency, just heat work divided by W by QH, this is efficiency. Eta max is this one red line. So as I said, it is bounded by this. Carnot is here. Anyway, you see that for non-thermal bath, the efficiency, this eta max, both can be above Carnot. But definitely it is bounded by 1. It cannot be greater than 1. On the other hand, see the blue line, it is above 1. That's quite, surprising. The point is, normally in classical thermodynamics, when you derive this, you just put these conditions of reversibility to use these bounds. Put these conditions, entropy productions is equal to 0, and then it's a reversible process. Based on that, you derive this. And it is equivalent to second law. If you use this, you get this bound on this Carnot, right? So the reversibility conditions for thermal bath also gives this bound. On the other hand, if you use the same kind of analogy for non-thermal bath, just implement this criteria of reversibility, you may end up with eta sigma, which is even unphysical, even greater than 1. It's impossible. So the whole point is that this derive a bound based on this reversibility criteria for non-thermal bath is useless. Okay, the maximum efficiency for such kind of non-thermal or whatever is based on not by the reversibility, but by the least dissipations over the engine cycles. That means maximum efficiency you obtain, okay, you have QH input, the least you dump into this cold bath, maximum you extract. On the other hand, if you put just use this criteria of reversibility, you may end up, there are papers which have ended up with this kind of results. It has been compared. So the reversibility is not, the correct, way to derive these bounds. On the other hand, for thermal system, thermal baths, the criteria of the reversibility and the minimum heat dissipations is equivalent. So therefore, in classical thermodynamics, whether you derive based on the reversibility criteria or least heat dissipations, they are equivalent. Okay. So on the other hand, for non-thermal baths, the situation is quite interesting. Okay. So that's it. With this, again we come back. I just mentioned this because so this is you give a sense on this generalized kernel. So you can have this eta max is essentially that GC, if you like, for non-thermal baths, which has to be derived based on least dissipation, not on the reversibility criteria. On the other hand, another example, the third example is very recently 2019. It is again on the ion traps, so where quantum flywheels has been experimentally observed. It is again some optical trap, okay, with the calcium ions. So again, this ions has in the valence cells it has only one electron. So so this electron spins is essentially acts as a working medium. Okay, now what they have done, so they put these ions in this trap. Okay, and it has an optical trap, so it has standing waves. So this standing wave, it is the x-axis. So these standing waves has this sinusoidal form. So it has nodes at the origin. So this is the Hamiltonian. This is how they model their system. So you have what is flywheel? Flywheel is essentially, okay, I'm just coming to that. Okay, so you have this sigma, H cross H bars omega Z sigma Z. That's your free system ions. It's a two-level spins. Then since the spins is also it is placed in an optical standing wave, and which mediates a coupling between the engine and the flywheel. So this is the optical standing waves with the amplitude delta S, and this is the wave number. It is coupled at the positions of this ion at X. So this is the kind of the Hamiltonian. Now the ion undergoes, okay, so harmonic oscillations. So this movement of this ion in this trap is essentially the flywheel. So flywheel in engines essentially stores energy for some time for future use. So this is the kind of analog. So the harmonic oscillators, because these ions, it's undergoing harmonic motion, so its frequency is changing or getting amplified. So this is how they model these harmonic oscillators. Then what have done, like this, they have these calcium ions. You have you know how to draw this. Okay, I do not have the energy levels diagram. They use some optical pumping at the trap frequency. So this optical pumping, okay, so this is like heating, because it's an auto 4-stroke auto cycle. So you have heating in 2 strokes, and you have another strokes you do not have any heating. So this heating is realized by optical pumping, and then again followed by cooling, and the temperature and the spin populations corresponds to temperature. Okay, so the spin populations, if you like, you have this ground state, and this very schematically you have these states. So you have these populations. Once you shine hot lasers, so it essentially excite the populations to the excited states. And then what happens, let's say this ion is here at the center. Once you have this pumping, okay, it gets energized, so it makes some motion along let's say positive x-axis. So it goes along these directions, and then again it comes back. When it comes back, it comes at the origin. Now you can have the temperature can be the temperature of this can be derived from the population. So the populations, if you like, in this circle, so these arrows is essentially corresponds to the populations of these various strokes. So for examples, here more populations is in the ground state. So the blue circle is larger than this one. Then once it changes, this is how these populations they have drawn. Okay, so mathematically you can calculate the populations by sigma z average. So it's a 2 level, so it is minus tan hyperbolic. This omega z prime is essentially the effective frequency of this one. So if it is a small wave number, then you have essentially this one. So it depends on the average displacement of this ion on this trap. Okay, so now as I was saying, like initially after hitting, ion goes to this one, again comes back, comes to the origin, and then it goes in these directions. When it goes in these directions, this x average becomes negative. So that means ions takes energy from the flywheel itself. So the flywheel, essentially, I mean this motion of this ion, which is essentially modeled by harmonic oscillators. So, but now you can think of, since it is takes energy, you can think of its energy now decreases. So the gap, okay, so that kind of, something input work on the system. So the gap decreases, okay, and then again in the third strokes you cool down. So now these ions is up to this, then you cool down, brings the populations in the ground state. So this is one. Again, once it approaches, 0, again due to this restoring force, and again it is again, get the momenta, and it again go to this. Again, the energy levels increases. So that's how this, this population changes. So you have in 2 strokes, you have this work input and the work, output. So depending on that, this is how they realized these cycles. So this is how one of the populations in the excited states oscillates. So you see that these high temperature, okay, so these bars are like these hot cycles, hot temperature followed by this one, cold one, blue one, and so on. So 3.5 millikelvin is something like the hot temperature. This is like this cold temperature, and this populations oscillates between that. Now here they because they calculate what is this energy and the ergotropy. This is what I just mentioned. Okay, and here they have a very good correspondence, and this ergotropy of the flywheel. Okay, so you can understand that this temperature can be calculated from this spin populations. So it is tan hyperbolic one, where omega z is this one. So the high temperature, if you like, it's the sigma z average is 0. On the other hand, sigma z average, so that means equally populated one. So that is high temperature. On the other hand, if it is all the populations in the ground state, so that's the sigma z average is -1. So that kind of low temperature. Based on that, they calculate the average energy. This is what they have compared and plotted with the experiments. Now, engine cyclic operations result in an. Now, what happens that if you do these processes, continuously. So what happens gradually? These oscillations of this ion eventually increases. So these motions eventually increases. So that's kind of this amplitude of oscillations increases. So that's kind of work if you can think of. So this is essentially stored in this flywheel they considered, and they calculate difference between this one, and they call ergotropy. This is they have compared. Okay, so this is and this is the last experiment. This is the last slide, and then I will conclude. Okay, so this is the last experiment I would like to mention. This is quite interesting because this is what they call it's a genuine quantum effects. This is from Oxford. Again, this is a theoretical proposal which has been verified. And this is interesting in the sense we have discussed various forms of engine cycles, starting from continuous in one limit, 4 strokes in the other limits. So what they have done in these experiments based on an NV-centered diamond. NV-centered is like you have a diamond, then you have a defect replaced by one carbon is replaced by nitrogen, then you have one extra electron. So that's kind of this working medium here. And it has 3 levels if you have this ground and the excited levels if you consider. So it is essentially a 3-level systems. Exactly, the theory paper also consider a 3-level systems. You have 3 levels, like SSD also have 3 levels. Now, based on a 3 levels, in this theory paper, they show some equivalence, that all these engine cycles are equivalent to each other. So that's the paper by Ramanujan. Okay, so and the experiments has realized these theoretical observations, again using this NV-centered, which is the 3-level systems, and experimentally verified the theoretical predictions. So what the theoretically, they have predicted that a real quantum effects, that is like quantum superposition of states, can have a measurable thermodynamic effects, and 2 such related effects has been predicted, like an increase in the output power with respect to classical engines. So quantum engines, as I said, you can have power output boost in various ways, like cooperative boost and that. Similarly, here also they have this kind of systems, have kind of output power boost. Okay, so that's, you can think of like a thermodynamic signatures, which has been experimentally verified, and the equivalence between these various form of heat machines in convergence of this output power in different form of engines. So the idea is the following. See, you have, when you have this, how do they realize theoretically? You can understand that continuous cycles, this red arrow is like a heating one, and the blue one is the cooling. Okay, and the unitary is like the work extractions, right? So this unitary dynamics is this one. So continuous means, like in SSD, since the system is simultaneously coupled, it is never detached. So that means this work extraction and this heating and cooling occur simultaneously. So that's continuous. 4th stroke, the other limit, you have first heating between ground level to this one, then you extract work in these levels, exactly like SSD. Okay, the signal, and again you have like cooling, and then you have this one. So that kind of, you can think of like a 4 strokes, and you can have in between 2 strokes. Initially you have both heat exchange and followed by this unitary strokes. Now what experimentally they have shown, like these engines are realized by these NV-centered diamonds in these and this, its ground state manifold, it's 3-fold. Okay, and what is important is that these spin states can maintain even coherence even at their room temperature. So that's what, I mean, quite interesting, and therefore they have chosen these systems for realizations. And then what they have done, like they apply a magnetic field. In presence of these magnetic fields, this one state even go below this the 0 state, so the +1, and it goes here. So then this optical pumping, so they make some optical pumping, so they excite it. So eventually from these 2 states, populations, eventually you excite, so some excited states there, and then eventually you allow you to decay. Okay, so this is a radiative transitions, and then you have, it can come in 2 different processes, come to these ground states. One is the radiative process, preserving, and another is a non-radiative one. So the radiative, if you like, this is relatively the more thicker one, dotted one, and this one has this purple one is the non-radiative. Okay, so the non-radiative comes through again some intermediate states, which is a singlet state, spin singlet state 0'. Okay, so it passes through this one. Now, so what happens, since in presence of these states goes below these states? Okay, now you can understand, since these states it's not populated, so this transitions is not essentially you can overlooked. So then entire systems you can reduced. Okay, so you have these 0' states and the lower 2 states, so that combines your 3-level system, constitutes your 3-level systems. Then what happens, because of these non-radiative transitions, the populations, you create a population inversions between 0 and +1. So you see that there is a population inversion, because because a higher rate of this non-radiative decay from this intermediate state 0' to 0. Okay, so results in a population inversion between these 2 states. And then what you do, okay, so you essentially pull the populations, now it decay to this state, so you have more populations, then you shine some coherent light, external electromagnetic fields, okay, which resonantly, excite between these two states, so that you get, more power from this one. So this is kind of, due to by exactly like you do, stimulated emissions of microwave radiation. So this is how they realized it. And they have shown that using these kind of setups, okay, now depending on how do you, these heat and heat strokes and these unitary strokes, you realized, okay, you can have all three different limits, like continuous 2 strokes and 4 strokes. So eventually they get a very, very similar behavior. So they called this is kind of, equivalence. And also they have shown, like particularly compared to this classical one, it's the quantum have, in terms of the power output, it has enhanced power output. So that's kind of, quantum superpositions plays some fundamental role and so on. Okay. So with this, I conclude. So as I said, I mean, there are, the applicability of this concept is, quite interesting. And there are various other approaches which I have not covered, like information theoretic, resource theory, optomechanical cooperative effects, measurements driven, and these thermodynamic uncertainty relations. So there are other, framework or, language there. So I have, here I have taken one of the language which is particularly, more relevant to this experimental situation and so that. So with this, I conclude. Thank you so much. Okay. Any questions? I think, this part anyway, I have stated the results. So. Start. Okay, the first one. Yeah, sorry. Yes. Okay, so tell me, what is the question? This one, yeah, phonon, yeah, number. Okay, so I don't think this is well. So you see, because it undergoes this kind of oscillation. So depending on, say, put some origin here and they put the number in, like this one. So otherwise, it's otherwise this is. No. Okay, I have not drawn. I have just taken these figures. Okay, let me understand. Well, so these what they have called is like this relative mean phonon number. Okay, so they have put 0 in between. Yeah. Okay, so maybe they just call this one kind of an high temperature. This is how they denote. I don't know. Or maybe they just scaled something. This could be like 0, then it would be like 1200, something like that. I don't know. Maybe okay. Maybe you can look at it. I will also. If I get it, I will tell you. Okay. Yeah. I'm not sure. The frequency, maybe I understand well, depending on this. Okay, I have to look at. Any other questions? In experiments, I don't know. Do they put it like that? I don't know. Those who are experimentalists, maybe you can comment. No, yeah, then this is a very strange convention. I don't know. Do you have any idea? Okay. Sorry. Oh, yeah. So relative mean. Okay. So maybe with respect to this one, or maybe in between.
Hello. So yeah. What is this? What they plotted? This blue one, the red one. What they plotted actually is the ground state they plotted, or that's or
Okay. No. They have these strokes, right? So they have like this isochoric and this isothermal strokes, right? If you look at yeah, here. So in general, it should be like this one. But as I said, this ion is not properly thermalized. Exactly what you are saying. Because in this trap, so this in this Starling case, it is much distorted. But in general, the curve should be like this one. Okay, so the isothermal should be like this, and should be isochoric. But what they have reported, it's kind of something like this one. Okay, so these are like very schematic. So what they have shown, like initially this atom is in the some ground state, so then they have this laser pulse which makes these widths larger, then essentially they weaken the confinement. Okay, so so then this atom goes up in the z directions, because this is, you know, depending on this confinement, it can go off, and this does this. So again, you have a laser cooling, it brings, okay, lower the temperature, then again you have a restoring force, eventually it brings something like this. Yeah, but anyway, I mean, technicalities is also, you know, complicated, you know. And what, with respect to how do they define this relative mean, so that maybe I have, all these things are both are relative, so maybe they have some reference frequency or reference number, so only then they get this number, negative numbers. Okay, anything else? So as you were saying, like since this here also this bath is realized by laser, I mean the electric noise, but it's a driven system. So I mean this experiment, they calculated this work output in 3 different ways. This is the first experiment. So one is the area under the curve. Okay, so from there they calculated. So it is, if it is an n omega plot, exactly this kind of definition, n d omega. So that gives some, you know, amount of work and divided, so that's power. One is the direct measurement, like since it's a, you know, damped harmonic oscillators, so based on that they calculate, measure the amplitude, measure the gamma damping frequency they know. So then, so they have also, they have some analytical, they mentioned something analytical equations, where they said, like since this ions is trapped and now they have various strokes, so eventually I mean it will feel some temperature dependent force. Okay, so they have, you know, temperature dependent force, essentially they have this, all these radial directions and this azimuthal phi directions. So they have thermal distributions, like they have considered, it's a 2-dimensional Gaussian distributions they considered, and based on that they calculated also analytically. And I mean, all these methods gives, you know, consistent results, and this is what they had claimed. Yeah. Okay. Okay, thank you.